Good morning, everybody. Today I'm going to talk about functional data analysis, and you have here the collaborators with whom I have worked on some of the things I'm going to talk today. Part of it is a review, and part of it is some new results. So I don't know how familiar you are with functional data analysis. Some of you may be more, some less. So I have a very brief review in the beginning, and then I'm going to talk about some things I have been interested in recent years, and also what is current research I'm doing. So in the functional data analysis, we are considering functions as data, and this is basically, to some extent, it can be viewed as an extension of multivariate analysis in statistics. The many concepts are in principle similar. There is only one real major difference, which is that in the functional data analysis we have some sort of a topology on our data, because there is an order and there's a concept of neighborhood, and therefore there's a concept of smoothness, which you do not have in multivariate vector data. And a typical example where you can see this is that in multivariate analysis in statistics, all the methods we have are permutation invariant. That means if you reorder your vectors, you get the same analysis. There's no change whatsoever, and that's not true here, because if I change the times of my functions t1, t2, then I disrupt the topology, the neighborhood relation, and the smoothness. And so that's the main difference. And that's where things get more interesting as compared to multivariate data analysis, which of course is well developed now. And there are different approaches in functional data analysis. The one I'm adopting here is that data correspond to independent realizations of a stochastic process which has smooth trajectories. There are people, other researchers, who view functions as fixed and not random, for example, and then put some structural constraints on those. There are several approaches which people are using. So this is not necessarily universally the case that you use the idea that these functions are stochastic processes. And what do we want to do in this field? Well, first of all, one has to think about means, variances, covariances, correlation. Regression is the topic I'm going to talk about today. So all the classical notions of statistics have to be rethought because there are difficulties in their definitions here. And the methods I'm using here is functional principal component analysis, for reasons I'm going to explain. Warping is something which is very important, but I'm not talking about it. That's very typical for this area, which you also don't have in multivariate analysis. Namely, your times can be also following a stochastic process themselves, and then you end up with two processes, a time process and the amplitude process, for example. This leads to more complicated but also very interesting and in many areas relevant models. So that's the warping topic. That's a whole topic by itself, which also recently has seen quite a lot of activity. And then, of course, you need regularization procedures because you are dealing essentially with infinite dimensional data if you talk about random functions. The tools are smoothing and differentiation methods. To some extent, estimating equations, some representation of stochastic processes, and then you are working basically in the Hilbert space L2 and working with linear operators in L2. So the classical theory of those linear operators also plays a role, but nothing is needed beyond, let's say, 1950 in that regard. So at least in the things I'm presenting or what I'm doing. So the applications I'm going to give are about auction data, and there are some other longitudinal, like genetic data. And I'm going to talk about functional principal components, and then the method to estimate them by conditional expectation, Pace method, regression models, and then the functional additive model, which is a current development, more current development. Okay, so the functional principal component analysis is sort of a basic idea which is used quite a bit by many people who want to do asymptotics, because if we do that, we have a relatively straightforward way into the asymptotics of this problem, which is more difficult with other approaches. So you have a square integrable stochastic process. Mean function and covariance functions are well defined. And then there is the so-called autocovariance operator on the covariance function. You just take the covariance function as your kernel. And you define this linear operator HE applied to function f in L2. So this is very simple. And then this operator has orthonormal eigenfunctions phi k with ordered eigenvalues from lambda 1 downwards ad infinitum. And the eigenequations, they look like this here. HE, the operator applied to the k's eigenfunction, is lambda k times the eigenfunction. And then, of course, the k's eigenfunction is orthogonal on our previous ones as side conditions. And so you have this sequence of equations by which you can construct the eigenfunctions and the eigenvalues of that operator. And the nice tool is then the so-called Cohen-Raff representation, which was published in 1947, for example, by Kahunen, and was, however, picked up by Grenander. He made it popular in a 1950 paper. And the representation just says that you can use the phi k's as a basis of your space, and you can represent any function which is in the space, including a random function in that basis. That's all this is. So we have I subtract the mean function mu from this expansion. I view the mean separately. You could also fold it into the expansion, because the mu, of course, is also expandable in that basis. So this is well known in multivariate analysis. You can represent any random vector in terms of its mean plus the principal components and the corresponding eigenvectors. So that's well known in multivariate analysis, and also holds here in the Hilbert space, holds basically just as a basis representation. And the only difficulty is if you sum to infinity, you have to watch what this equality here means, etc. This is not really relevant here. And the coefficients here are our random effects in that model, which can be expressed as inner products between the eigenfunctions and the processes xi. They are uncorrelated random variables, and their variances are the eigenvalues, which have to be summable because the thing is L2 is square integrable. So this is all very well known, and Grenander made ample use of this in his 1950 paper. The problem, of course, in 1950 was that there were no computers to speak of. And therefore, Grenander had sort of the insight that you can use this to do a lot of things, including functional regression. In fact, the functional regression model appears in Grenander's paper. But he had in mind a sample size of 1, so he didn't really have in mind statistical analysis. He had in mind just modeling stochastic processes, but not applying that in any meaningful way to statistical analysis. So the paper is very interesting, and it has far-reaching ideas, but they couldn't have been implemented at that time. The first one who really tried a statistical implementation of this was Rao in 1958, 8 years later in the context of growth curves. Very rudimentary ideas, but nevertheless a very interesting paper too. And then the so-called modes of variations, which are just the eigenfunctions, were made more popular later. 30 years later, basically, when the computing was up to snuff to this day, these people published paper in Technometrics, and then there were a rapid sequence of papers. Rice and Silverman is a landmark, the 91 paper, where for the first time more sophisticated statistical methods were used, and then there's this book by Rice and Silverman where they advocate pre-smoothing of the individual functions or observations which lead to the functions, and then going from there. Now, why do we do the functional principal component analysis? Because there's a straight equivalence between your process X and a countable sequence of principal components, and that's a big advantage. So we go from an infinite dimensional object to a countable sequence, and we like more to deal with countable sequences in some ways. It makes things easier. And more importantly even, is that any function f of x can be written as a function g of a1 to a2, etc. So whatever function you have in mind, including regression functions of your stochastic process, can be written as a function of this course. And oftentimes this representation is much more advantageous to the f of x representation. That's why principal components are a useful tool in this area. And now the problem, of course, then is if you want to use principal components in this area, the data are not usually functions. Also, there is again there is sort of a division in the literature. About half the literature assumes that you have functions, which, however, is quite unrealistic because there is hardly any case that we have functions. First of all, of course, strictly speaking, a computer cannot represent a function by only a vector. That's maybe more a theoretical distinction, but there's a really solid statistical distinction, which is that whatever you have, there is noise and there are errors, and so the function is usually not observable without noise. This is the rare case that you observe a function without noise. In most cases, you have a noise. And even more cases, your points where you have the measurement of the function are not very regular because of missings or missed appointments in longitudinal studies of patients who don't show up at times when they're supposed to, etc., etc., etc. You have usually quite irregular designs, TIJ, that's the points where we make the measurements of the random function. And therefore, to assume that you have the whole thing available is an illusion which is not very, which doesn't get you very far. If you want to do real data analysis, you have to realize that first of all, there's an error. And secondly, at a minimum, you have some sort of a problem with your measurement times, which are not regular. So basically, the idea then is to plug this in, to plug the irregular time points into your model and also the error, so that your real model then looks like this, that you have the cardinal F expansion here, but not at small t, but at Tij, which are your measurement times, and there's also measurement error. I assume here that the measurement errors are IID and independent from everything else, and also that the measurement times Tij are random and independent. They are not IID over I. That means different subjects can have different distributions for those measurement times, but they would be independent for what I'm doing from the rest. So for me, these are random variables. The times of measurements are random time points. So here is an auction example where you have data like this, and where many people have been interested in recent years to apply functional data analysis methods. The typical data look like this. So this would be 4 auctions from eBay. What happens here, with some trouble, you can recover those data from the eBay websites. It's actually not so easy to do that. So these data were actually recovered in the old-fashioned way, that somebody followed up and recorded by hand. But the eBay makes those data available either for a hefty fee, or you can get an academic account, and then you get some kind of not very convenient data to access. So it is a bit of a trouble to get this data in an automated way. Nevertheless, there are millions, of course, of auctions going on every day. So you can appreciate that we have hundreds of millions of such data available, and so there is ample space to do data analysis, and here functional data analysis. So what people have been doing to a large extent so far is they smooth those data with some pre-smoothing. Let's say p-spline is very popular. P-spline smoothing, you get some smooth function, and then once you have that function, you do functional data analysis. And I want to say that's not the right way to do it. You actually should take into account that you have random times here. There are gaps in the bidding. So these are the bids which come at those times here. The auction here are 7 days. So this goes to 166 hours. And this is on the log price scale here. So this is a log scale of the bid price. Start low. Sometimes you have some sort of actual discontinuity here. And then what is typically is there are gaps in the middle of those biddings where nobody is really interested to bid. And then at the end, usually many people wake up and try to get a good price at the very end. If they see something is low, they place a bid. This is called bit sniping. So it's very typical. You have very dense design here, and in the beginning also often, but in the middle there's not much going on. And so there's an interesting actually data problem, and recently generated a lot of interest. So I use this just as a motivation for the fact that I view the TI chatter times as random. So here we would have a U-shaped density function because there's less bidding in the middle, and both ends have heavy bidding. So my density of bidding is U-shaped. If I use this TI distribution, it's U-shaped. So how do we handle this if we don't do pre-smoothing? Well, the idea is that you want to estimate, first of all, your kernel, the covariance kernel or covariance surface, G of ST. And that you can do by just pulling all the data together, assuming that this is the same across subjects. And you calculate the raw covariances for all pairs of times, and then you smooth this across the board. And finally, you have to project your initial estimates on the space of non-negative covariance matrices or covariance surfaces, because the thing has to be non-negative definite. It's a covariance after all. So you have to take care of this. So the advantage of this is that you can confine the measurement error onto the diagonal, because it's only, since my measurement error is assumed to be uncorrelated, I can then confine it entirely to the diagonal of that thing. So omitting the diagonal in my data just takes care of the measurement error if this assumption is correct. I completely cut out this ridge. I just don't take the diagonal, and the smoothing method doesn't care about this. It's nicely consistent across that ridge, even if I omit it. So the measurement error is cut off. If it's really uncorrelated, it's completely gone with this procedure. While if you do pre-smoothing, you convolve your measurement error with everything else, and it will show up in your covariance structure. So this is a mistake in that regard. While here you can just cut it off. Now, we need actually, when we do this, in order to do the perturbation theory, we need some sort of convergence of the surface, the estimate surface to the true one. And there have been two sorts of results for this. One is in the L2 norm, and the other one is in the subnorm. And you get different rates of convergence. You have to be a bit careful with those proofs because you have dependent data. These covariances are not independent. So one has to modify the usual knowledge of smoothing methods, which are for independent data, a little bit to take care of the mild but present dependencies of those raw covariances. And not only do you get a covariance estimate, you also get an estimate of this ridge. If it's constant, for example, you can just take the base, which you estimate from the covariance, the base of the ridge, and then you can look at the diagonal itself to get an estimate of sigma squared. And in fact, this noise also provides a certain regularization, as I will show you in a moment. It's actually an advantage to have it on this ridge. Anyway, so once you have that surface, then you estimate eigenfunctions and eigenvalues by solving this equation in a discretized way. That's the eigenequation again. What you do is you discretize this and you use an algorithm from numerical analysis, your favorite algorithm, and then you project on the space of positive definite or non-negative definite, I should say, covariances by just cutting off everything which has been estimated with negative or zero eigenvalue. It's as simple as that. One can show that this is actually the best projection you can do. Okay, so then we want also the random effects because we want to model individual functions. So we need to get an estimate for the AI case. That's the principal components or principal components course. They are defined by these inner products because we are in the L2 space. Now, the natural thing to do is to write this as an integral here. Approximate this by an integral. This works well if you have dense designs. It doesn't work if your designs are sparse. That means that Tij are random. Then we cannot actually assume that this integral is close to this. In fact, it will not be. So there's a numerical problem if we want the AIK. And therefore, we use this PACE method, which means that we replace the integral by conditional expectation. So we just use the conditional expectation of the principal components core given your data for that subject, or for that auction for that matter. And this is what you should do in the Gaussian case, or you can do explicitly in the Gaussian case. Otherwise, it's the best linear approximation if it's a non-Gaussian case. what happens here is, here you can explicitly calculate this. This is an interesting regression because the UIs have a different distribution for each subject, and there are different number even for each subject. So it's not a standard regression here, right? The UIs are varying from subject to subject. One subject has 2 measurements, another one has 50, etc., etc. So the UI are by no means equally distributed. And therefore, you have to, it's not a simple regression here. It's something where I can write this conditional expectation explicitly, and I can estimate the elements of it. And we need to invert the covariance matrix of the U's. That's a little bit of a trouble. That's why I write generalized inverse here, because this inversion requires some sort of a regularization. The measurement error on the diagonal, which I showed you, it provides already a ridging, actually. It provides a ridge regression. And in fact, sometimes we need to ridge a little bit more than what this already provides to make this happen. So you can then, in any case, get an estimator of this conditional expectation, which is consistent, and it works quite well as a substitute for the true conditional expectation or for the true principal components course, which you don't know. So interestingly, if you do this conditioning, and you compare it with the integral, you can prove that the conditioning converges to the integral if your design gets denser. So they are actually the same in a dense design, which means the conditioning you can do always, whether you are dense or non-dense. The conditioning and the integral give you the same thing if it's really dense. And we have implemented this in a program which is actually available from our website. And I show you now how this works on the auction analysis, which is a preprint currently. This is the so-called design plot where you use all the pairs of the times at which auction bids have been observed. We need to make sure that this plot covers the whole square without big holes, because the smoothing is going to apply to this. Remember, I calculate all pairwise cross covariances, raw ones, because I don't have repetitions. They are all single values, so they are not consistent themselves. And these pairs have to cover my domain squared, the square domain, which they do nicely here. So that means the method can work. I can smooth this. The diagonal here will be left out in that smoothing, so it's not included. And then you can then calculate the mean function up here, also pulling all the auctions together. So that's just the overall mean of all auctions. And then you get first, second, and third eigenfunction. You have to think about how many eigenfunctions to include. That's that model parameter 2. And that one is done here by a pseudo AIC criterion, meaning that you pretend the data are Gaussian, which they probably are not, but and then you write a pseudo likelihood, and then you put the penalty, whatever your favorite penalty is, on it. So that's how you can find relatively good method to select a number. Alternative is cross validation, but cross validation does not work that well, it turns out. So these pseudo criteria, pseudo likelihood methods work better in practice. And this would be the fit for the 4 auctions I showed you before. The point here is that the smoothest assumption may not entirely be appropriate, because we have those kind of maybe discontinuities in this data. However, since we have smoothest assumption, it will fit a smooth function, a smooth auction price curve through those on log price scale here. And so that would be your fitted auction trajectories, the price trajectories for this 4 using this method. And the classical method, as I mentioned, would be to smooth the entire predictor trajectory. I don't have to show this actually. I have already shown this. So let me move to the next topic, which is the functional linear regression model. As I mentioned before, in its core, the model appeared already in 1950 in Grenander's paper, but it was put up in a statistical context only in 1991. That means 40 years later by Dalzell and Ramsey. in which they, which is the first paper to bring up this so-called functional linear regression model, which I write here in a statistical context. And so what happens here is we have two models which I'm considering, one where the response is a scalar and the other one where the response is a function. I'm actually more interested in the case where the response is a function. So I will talk more about that, but the differences are only minor. So what happens is that you have a constant here, which is your mean function. Then you have the centered predictor process. You subtract the mean function. And the beta is your regression parameter function. So it's a fairly straightforward extension of the usual linear regression model. And here, the case where your response is a function y of t rather than a scalar y. And so what we are interested in then is to estimate this function beta, which is an inverse problem. And sometimes we also have non-functional covariates, which would make for more interesting models, because you need then to extend this to add more predictors, which are, for example, non-functional. Or you can sometimes have several functions rather than just one function x. So there are all kinds of variations of these basic models. And one thing which is of interest oftentimes is the question about changing domains. And that also applies here for the auctions, because the domain may vary from subject to subject. This can be called the eigenfunction evolution. This actually happens in biodemography also, where you have, let's say, egg laying for a fly on a certain time frame, and the time frame is increasing, and you want to predict the remaining lifetime while this time is increasing, things like that. So here I'm interested to predict the final auction price, for example, with a functional linear regression, and I want to know how well can I predict as the auction is moving forward over time. So the idea is very simple. You assemble all similar auctions which have been observed to a given time, the one time you assume you have interest in. So this gives you then a plot like this, so that here I say here that I observe the auctions only for the first 24 hours. And I assemble all the auctions, all the beginning parts of those auctions, and calculate my three eigenfunctions, the mean function. Then I assemble them to 72 hours, assemble them to 120 hours, and so on. So you can see that there is a sort of a smooth eigenfunction evolution, in the sense that these eigenfunctions change smoothly over time t, as does the mean function. That's what we call the eigenfunction evolution over time. And there are, by the way, all kinds of domain changes, not just forward in time. It could also be that your domains are changing in a different way. They can change, both ends of the domains can change in some applications. So there's a real issue here with the domains of your predictor and of your response, because maybe you want to predict the second half of your function from the first half while time is moving. Here I predict only a scalar, but I may also want to predict, actually by functional regression, a second half of a random function from the first half while the time is moving from 0 to the end. Right? So then my time on the response function would also, my time domain on the response function would also shift according to some scheme. So there's all kinds of such combinations of interest. So if you then look at the functional regression for this situation, then the prediction error, one leaf out prediction error, is plotted here as time goes on. The one I get when I fit a functional linear regression model for the final price of an auction, log price to be precise, given what I know by up to time t here, and given that I want to do a functional prediction by using this linear regression model. So you can see that in the beginning, the information is pretty low up to at least day 70. Then you get maybe a little bit better. It seems to have a step here, then a step here, and then you get even better here. And then finally, you seem to gain quite a bit of information towards the end. This one here actually is the so-called bid sniping phenomenon, justified by this, because people just come in at the end when they know where the auction is headed. That's what That's what this tail here shows you. You know much more about the final price. Okay, so the idea here is, generally speaking, is, and that applies to a lot of functional data analysis methods, that we get inspired by the multivariate situation. This is the multivariate normal equation, the population normal equation for multivariate linear regression. B is a matrix, parameter matrix. This is just your normal equation. And this normal equation is generalized to the functional normal equation. That's how it goes. Here you have the cross covariance function, the autocovariance operator I mentioned before, and then beta is your regression surface. That's the case where y is a function and x is a function. And the problem arises to estimate the beta is that we have a functional generalized inverse. You need regularization to get it. The operator H is compact, so it's difficult to invert, and therefore you need to either do some truncation or penalizing. Other regularity methods exist. So you can theoretically write down generalized inverse in terms of the principal components course if you want to. And however, to get that in practice is a different question. Okay, so the functional linear regression is can now be represented explicitly under certain assumptions as follows. I consider the case where x, the predictor, is a function, and I express this predictor function in terms of its principal component expansion, and y, the response, is also a random function which I also express in its own expansion. And the model is here. So this is our model, and then I write down the normal equation for it. And if I do this, I can actually find an explicit representation for the parameter function surface, if you wish, because it has two arguments. T is the response argument, S is the predictor argument. I can express it explicitly in terms of the predictor eigenfunctions, the response eigenfunctions, the covariances between predictor and response scores, and the variances of the predictor scores. So this is a very straightforward representation. Of course, summing to infinity is not working in practice. I have to now regularize this somehow. For example, truncate just by taking the first finitely many components here. And if I write this, then I can see that the expected value of my response score BM, that's all I need to calculate this regression, given x, the predictor function, is some beta mk ak. So this is immediate from this. And the expected value of the response score given any predictor score is very simple to calculate. You just expand this conditional expectation. And since the A's are uncorrelated, and I have a linear relation, EBMX is linear in A1 to AK, then of course the conditional expectation here is just a function of AK only. So that what happens is, what I see from this very simple consideration, what I see is that the regressions of the response scores of the predictor scores are all simple linear regressions through the origin, in fact, because the means of AK and the means of BM are 0. Remember, these are principal components. So these are all simple linear regressions through the origin, which makes this a very simple approach. In some ways, just simple linear regression applied many times. I have here some remarks. Other basis representations have been considered. For example, wavelets and also B-splines. The eigenrepresentation has the advantage that since we have uncorrelatedness of the scores and independence even in the Gaussian case, which makes it very convenient to work with those, and also which gives us this simple linear regression interpretation, which allows all kinds of diagnostic procedures, for example. And also, this is usually the representation itself is very sparse, because in most cases you need not many predictor scores. You need maybe 3 or 4, it turns out in practice, simply because your eigenfunctions are already adapted quite a bit to the predictor and the response functions. They are not adapted to the beta. That means your regression function are not adapted to that. The beta theoretically needs infinitely many to be fully expanded. But in practice, it turns out that we usually need only very few. There's rarely a case where you need more than 10 components in order to fit such a functional regression. And the other advantage is that you can do the sparse predictor case, let's say the auction data or data like that, where you don't have many observations. The observations are sparse and noisy. And this all can be nicely incorporated in this principal component approach. And finally, we can also select a number of components very easily by this pseudo-IIC or BIC criteria. Inference is not so easy, of course, and there is not many results available. The only method which one has for inference right now really is bootstrap. There is no alternative to it. And the bootstrap can be implemented in various ways, some faster, some slower. We have done some experimenting with bootstrapping in this area, and I'll show you some examples of this in a moment. Here is an example for gene expression now for Drosophila, where you have microarray gene expression time courses, 66 time points for Drosophila life cycle. This is a well-known data set. Many people have analyzed it, publicly available. And we use here a subset of 21 transient zygotic genes. These genes have all been assembled already into certain groups which have biological annotations. So I take a subgroup of those genes, and I want to run a functional regression in the following way. I take the pupa phase, which is just before the adult expression, and want to regress it on the embryo phase, which is the beginning of the Drosophila larva. It starts as an embryo and then at some point becomes a pupa. And so the question is, what can we say about pupa expression? How is it related to embryo expression for that particular gene group? So I'm viewing those genes as independent functional predictors and responses which correspond to each other. And here you just see a plot of all of those 21 functions, predictor functions, response functions. Red curve is just a mean, the overall mean. And then the next step would be for such a regression that I calculate the eigenfunctions according to some criteria which I need for the regression here, which tells me that I should use 3 predictor eigenfunctions and 4 response eigenfunctions, which have been calculated here. At this point, you could try to interpret those, but they serve mostly just as basis functions to represent the regression here. And some other things I want to do then is if you want to convince, let's say, biologists or people who do applications to use these things, they need to have 2 things. They care about 2 things which they need to have. They want, of course, some regression equation, that's fine, but they definitely want the R-square and they definitely want a p-value. These are the 2 things they want. And so in order to provide this, then you have to think about what is a R-square which you could come up with here. It turns out that the R-square, that means usually the fraction of variation explained by the regression. That's how biologists understand the R-square. That this R-square is not canonical in the functional case, actually even not in the multivariate case, which means you have many ways to define your R-square. There's not just one way, there are many ways. We know that the R-square in the regular regression is the variance of the conditional mean divided by the variance of the response. Okay, so it's just a quotient inside this integral. That's what it is. But how should you extend that to the functional case? There are at least 2 ways you can see right away. One way is the one which is written here. Now you integrate the numerator and you integrate the denominator and you divide by each other. Another way would be I write a big integral here in front. That would also be a functional R-square. So the fact is that this thing is not unique. You have to come up with something which works, which is the most reasonable one. And there are quite a number of different ways to define an R-square here. We have settled with this one because it seems to work well in practice, and we can also prove that if you estimate this from your data, first of all, you can represent this thing in the eigenvalues of the response process and the R-squares of the individual simple regressions. Remember those simple regressions of response scores versus predictor scores. Each of those simple regressions has a R-squared itself. And the weighted average of these R-squares gives you the overall R-square. If you choose to define your overall R-square like this, that's one advantage. So this is just the weighted average of the simple linear regression R-square, which are very easy to understand and for every applied statistician very clear. So the interpretation of this is take a weighted average of your simple R-squares. And secondly, we also know how to estimate this consistently from the data, because of course these things are all unknown. You have to first come up with estimators and then show that these estimators converge to the target. So you have to prove that these R-square can be consistently estimated from the data. And so in that regard, this particular definition has some advantages. That's why we have been using it. And the second thing is that you want a bootstrap, that you want a p-value. And for that one, we only have to offer a bootstrap right now. So for this kind of regressions, you get R-squares like this and p-values like this. So biologists would then at least be happy to have those values. So there seems to be, in this particular case, there's a clear relationship between the response and the predictors for this gene data. And the second thing we like to have is the diagnostics. If we do regression, we want diagnostics, and you can do functional diagnostics. Similarly to this idea, by weighting your diagnostics from the simple linear regressions, you can do weighted diagnostics. And you get plots like this. This would be a functional head matrix, and this is a functional Cook distance, which is just coming from summarizing all those simple linear regression diagnostics together in a weighted form. And then you can provide such plots, and you can single out predictors which seem to be a little bit strange in terms of their Cook's distance, like this one. So I would then go back and look what is this predictor actually doing. So these things are quite helpful in functional regression as they are in usual regression. And so all of this can be very easily done if you use the principal component approach. That's basically one of the advantages. That we get all those nice plots which we are used to if we do some sort of applied regression analysis. Here is a confidence plot for the regression parameter surface. Remember, there is this function beta st, which provides me with the functional linear regression. And the estimate is in the middle, the surface in the middle, and then you have here the 95% pointwise bootstrap confidence bands. So for each point, you just calculate, you have the bootstrapping of this procedure, and for each point, you just calculate 95% confidence in a band, then you get the upper and the lower. And also this provides you with one further benefit, this plot. You can actually then look for those areas where your regression surface is not very different from 0, which tells you to cut out certain areas of the predictors which do not have a bearing on the response, because maybe not the whole predictor domain is relevant. And in fact, that's possible, and you can see here 0. You can find area here where there is no significant input of the predictor, while there is a strong input in the tail, for example, also at the beginning. So it is possible to pass down the predictor space actually, and you can even iterate your procedure. You can pass it down here, work with a new domain, and iterate a procedure until you have a very small domain. This works to simply reduce the number of measurements you would have to make. So if a biologist says they don't want to measure 50 time points or what, only maybe want to measure 10, then you can tell them which 10 they should measure based on this, because we can pass out the relevant domains based on such a plot. So that's another advantage to do this. So now I'm coming to the last part, which is extending the functional linear regression model. The functional linear regression model, yes, please.
When you say bootstrap plot, there are many ways to bootstrap a regression model.
Right. So the bootstrap.
Bootstrap or residual, or.
Yeah. Right. No. This is basically the bootstrap based on a sample xi, yi. xi being a predictor data, so in this case not a predictor function, it's a whole subject is left out. We take the subjects, we take the xi subjects, the predictor subjects. Well, you have pairs, predict and response from a pair, right? So we take those pairs as subjects and those pairs as data, which consist of, in this case it's regular, so they consist of the 18 predictor time points and 15 or so response time points, right? And so you leave out, you assemble those and you resample from that, you resample from the aggregated pairs, and that's if you want to construct this thing here. That's how this has been done. So it's a very straightforward empirical method. Bootstrapping from the residuals would be difficult here because it's not clear again what should be your residuals. In fact, so one has to think about it. Yeah, I mean there is a notion of functional residual. Actually, in that paper we have. In this paper, we have discussed also functional residuals. And your residual itself is a stochastic process. So it's a little bit cumbersome. The residual is not, it's itself a stochastic process which has certain properties. That's kind of the problem here. And so it seems more straightforward just to take this, that sampling bootstrap. Okay, so now the the functional linear regression has been the mainstay for the last, since 1991 when Ramsey's paper appeared. So that's about almost 20 years, not quite yet, but that has been the mainstay of this field, and there have been not that many alternative developments. There has been only one main alternative development by, let me say in apostrophe, by the French school, which is that you go back to the drawing board. I mentioned before, so you say Ey x is g of x. Okay, that's of course, that's our starting point. Here is our starting point, and in the functional linear regression model, we are willing to make a very strong assumption on the nature of the G. And what if we don't want to make that? Well, there is a so-called non-parametric approach, which means that you try to do a non-parametric regression. You may know how to extend a simple linear regression to a non-parametric regression, right? And so what I have talked about right now was only simple linear regression, nothing more. So if you want to do a non-parametric regression, then you can try to model this function G completely non-parametrically. And there's a book, I think it appeared 2006, Ferrati from Toulouse, who in fact developed such a theory. The problem is that if you are not very careful, you get super slow rates of convergence. Actually, even the processes where this thing will converge, if you do a certain trying to do it completely non-parametric, even the process where this is converging is kind of, let me say, a little bit tough to define which process will work. And we are just now working on a paper, three of us, Fang Yao, Peter Hall, and me, on a paper where we try to characterize this general model a little bit better in terms of, again, the principal component analysis. That has not been done so far. The French approach is a little bit different. Over there, it has not been embedded in the principal component framework, which seems to me is the reasonable one, because as I mentioned, the G of x is f of a1, a2, right? So we want to take advantage of this. It's a very straightforward, it's very clear that you have one way to do this, but you can at least try this and then try to still do it non-parametrically. Now, the approach which we have already developed before is that if we look at this here, then we have one simple way to move forward, which is additive model. So what we do is then we write this as sum fj of aj. So that's the thing I'm going to talk about now. This one is ongoing work I'm not going to talk about today. Actually, the paper is actually just finished these days. So we have an approach following in this way, but I'm even structuring more right now. I'm going this way. So there are many intermediate ways you can do functional regression. And that's actually interesting because it has not really been explored to the extent which one can do it. So here, I'm talking now about extending the functional linear regression model not to the most extreme generalization, which would be this one here, where you just say G is some sort of a smooth non-parametric function, whatever it is, but to the case where I'm modeling additively. So I take this point of view here, but then I say, okay, I look at the functional linear model. This is here again. You have seen this before. This is just a thing written again. And then if you look at this long enough, you wonder why should it be like this. You could simply replace this by a non-parametric, by smooth functions FKM, which each are one-dimensional. So that should be fairly easy to identify then, because we know very well how to estimate a one-dimensional function if it's smooth. Okay, so that leads to the functional additive model then, and I'm presenting here this for the case where predictors and responses are both functions. You have of course a simpler case where the responses is just a scalar. So here there is again a very simple consideration which makes this super simple actually, this model, which is the following. Look at the conditional expectation of the response score given the predictor score. I showed that before in the linear case. Now here we are in a nonlinear case. Okay, I do the same conditioning, double conditioning here. And here I want to model this now by some functions like this, right? So in HA. Now this conditioning step here is not as trivial as before. It's just one step less trivial. Before, I could do it based on uncorrelatedness. You remember that if this is linear in HAs, of course, this is just a function of IK. If it's uncorrelated. Now, that's no longer the case here. However, if I have independence, then it's still the case. So I need to now require independence of my principal components rather than uncorrelatedness. The uncorrelatedness I have naturally. The independence requires me to either require it or to say I have Gaussian model, right? And Gaussian model is always independent. So if I'm willing to make Gaussian assumption or independence assumption in general, then immediately this conditional expectation breaks down to just FKM of IK. So I'm back in the same as before, which makes this very simple. I don't need to do any backfitting or whatever for the additive model. That's a big advantage. I can just do a scatter plot smoothing separately for each component. The normal additive model is fraught by backfitting algorithms and their ramifications, which makes theoretical analysis very difficult. This one here doesn't have that problem, simply because of the fact that my predictors are independent. That makes a whole world of a difference if I do additive modeling. And so I can now just implement this by one-dimensional scatter plot smoothing. And for the gene data I just mentioned, if you use the one leave-out prediction error, you get a slight improvement if you move from linear to this additive model. Let's say in the 25th percentile, it's not really noticeable. The median shows a clear improvement, and a higher percentile also. The mean shows some improvement. The R square, whatever it means, that's a function of R square. I would discount this a little bit. That doesn't mean that much. Anyway, so there is some improvement here, and here is the plots which you get for the regression I mentioned. So you have 4 eigenfunctions in which you model your responses and 3 in which you model your predictors. And therefore, you get 12 plots to look at. And you have in each plot, this is first versus first response score versus first predictor score. In each plot, you have the linear model, which is just the simple linear regression through the origin, the red dashed line. And you have the smoothed one, the non-parametric one, which is the blue line. And so you can see that there are clear differences, but some of those differences are clearly driven by marginal points in the boundary. So leverage points Around here is one, for example, or this one. Sometimes the relationship is really linear, like here. Even here it doesn't differ all that much. However, the differences are enough to bring our prediction error down by about 10 to 20%. So this model works, gives us better prediction here than the linear model does. And you can also do asymptotics. That's a big advantage of this functional additive model. The asymptotics here also has relatively good rates, while it will have very slow rates for a general model like this. In fact, if you don't do anything carefully, you get rates which are almost double log over n or something like this. It's extremely slow. So almost close to the border of being useless. Here you can do a little bit, you can do some more interesting things by just proving with methods which already are sort of available. You just combine them. There are two key steps in proving the asymptotics. One is the perturbation analysis for the linear operators. That's pervasive in the field. You just have to compare the difference between the operator HE, that's the autocurrence operator, and its estimate, HE hat. That's everywhere. And secondly, you need to look at the predictor scores and the response scores, because you estimate them from the data. They are not really the true ones. So you have non-parametric regressions with errors in variables, because you estimate your predictor scores, for example. And so if you do the additive model, here these HAs are estimated. They have an error. So you have to take that into account. These are the two key steps. If you handle that, then you can put these things together and you get an asymptotic result here. So this brings me to the end of the talk. So in this field, I believe there are many open problems still. Multivariate curve situations where you have for one subject several curves have not been well investigated, for example. Also, there are many such data available. Covariance and correlation is a notion which has been attempted by many people, but in my opinion still has not been resolved to a completely satisfying way, including the warping issue which comes in here. You have warping. That means time distortions, which I didn't mention at all here. Then the auxiliary parameters, the choices of them have not been well investigated. Smoothing parameters, number of components to be included, etc., etc. Inference and asymptotics, many open problems. How to optimize the regularization, and as I mentioned, the warping is a big issue where many people have attempted to work something out, but I believe it's far from being settled. Thank you very much.
It seemed, going back to your auction data, that the log of the price was increasing with time, but did your estimation method didn't use the monotonicity at all?
No, it didn't use the monotonicity. In fact, you can do some shape-restricted modeling here, but my feeling is that it may not be really worthwhile actually to do it. First of all, you occasionally obtain non-monotone fits. Especially what we are doing now is we have extended this to the dynamics. That means you look at the derivatives, which is another topic I didn't mention at all. There's also the topic that you include derivatives of such functional data. Jim Ramsey has worked on this extensively, but there are some basic issues which start with the fact how should you estimate derivatives from data such as the auction data. So the available methods for derivative right now are this, and that's what Jim Ramsey and actually Jim Ramsey has not done that, but the auction people in apostrophe have done. They fit p-splines or smoothing splines and then take derivatives. Okay. And then in those derivatives you will see that occasionally you get negative velocities, which you should not have, right? So it would be probably, one way would be to look into this from the point of view of constraining the derivatives, and then perhaps integrate back to get monotone increasing functions. So the derivative is a very interesting topic right now in this regard. There are many ways one can, of course, take care of the shape restrictions. I find all of them lead to biases. That's a problem. So you have basically, I think there's a basic trade-off between increasing your bias and satisfying your shape restriction. Unfortunately, there's no free lunch in that regard. So even though the shape restriction is satisfied, you can't really enforce it without having to pay a high price for it. That's the impression I got. I mean, we tried some very simple things like power and stuff like that.
It seems in that case that you have basically two change points, right? First they bid and then they after
Yeah,
some
actually,
time,
yeah, that's not so common. The appearance of this sample is a little bit deceptive. That you have one time where a lot of bits shoot up like that is not common actually. So I don't think that this is a data which commonly has change points. There are some, one should probably say some of them have change points. But there are many others where you don't see anything like this. A majority actually doesn't have it. So it's not really a data where jumps are customary. Let me put it that way. Yeah, I know, but I regret to have selected those actually. This is a poor plot selection, I believe. So I know it appears, and in fact there are these jumps there. But it seems to me, if you look at all the auctions, I didn't show them here, it seems not to be a pervasive feature. It's rather an occasional feature.
Other question. I think this famous French school, didn't they prove something for asymptotic distribution of the linear regression estimates?
Yeah, there's a paper in a Zeitschrift, if you refer to that. Probability theory related fields.
Vaguely.
Yeah. Right, but one thing is that those results are all for a situation which doesn't pertain to the data I'm interested in, namely to the situation where you have completely, you assume your data are already the random trajectories and they are basically just given to you. This makes a lot of the analysis much easier. For example, in this case, if we have that, our eigenvalues can be estimated as square root n rates and stuff like that. So this has extremely advantageous situation. If you assume the whole process, it's a different asymptotics from the one which I'm presenting here, where we assume, for example, one assumption here I didn't really point out is that the number of measurements you have is a discrete random variable which is finite, the number itself, let's say Poisson or something like this. So the asymptotic for that situation is quite different than one where you assume you have given the whole random process continuously. There is no issue then of measurement times, there's no issue of measurement error. And you can, for example, get the coherence kernel US. Pardon?
And then it's almost your number of observations is so that you fix it, it'll go to infinity.
It is already infinite because you have the whole process.
Yeah, if you have the whole process, but in your situation you won't have it, right? So can you ever get consistency then?
It depends what consistency you are asking. You get, of course, consistency for the kernel eigenfunctions and eigenvalues. And for individual trajectories, you get consistency for the conditional expected value of your trajectory. So what you are aiming at is the expected value of the trajectory given the data. So that's the consistency is for that object. It is not for the actual trajectory. That one is not recoverable. It is the expected value of the trajectory given the data. That one is recoverable.
It would be a common trajectory, right?
Pardon?
It would be a common trajectory.
Yeah. It is a...
The common trajectory, I mean, they all have the same mean trajectory.
No. Individual trajectory given the data for that auction. That's what I showed before. I showed before. Okay, let me go back now. Oh, here. These are recovered individual trajectories. So these are recovered through the conditional expectation. So what I'm recovering is E expected value of the trajectory given the data I have on the subject. That's the object I can recover. I cannot recover the actual trajectory. So the difference between the conditional expectation and the actual trajectory is not recoverable. So that's lost, but I can recover consistently. So there's a consistency result for those trajectories here, the ones I show here. However, the consistency is given the data I have for this particular auction. Okay, so the consistency is strictly for that.
Is there something beyond consistency?
Is there
Something more developed than consistency for this problem?
No, not that I know of. I mean, you have a rate of, you can get a rate of convergence for that, but you mean like a normality or something, or what are you thinking about?
I wonder what is the state of the art, what is it?
Yeah, consistency is the state of the art. Rates of consistency, rates of convergence.
And what are the best rates?
For that one is not known. For the covariance estimation, under certain scenarios is known. Under certain scenarios is known. For the kernel, you have an optimal rate of convergence. For the individual trajectory, I'm not aware of any result along this line. For the kernel and for the mean function, yes. I mean the covariance and the mean function.
But here you have two smooth. In fact, you have two smoothness. One of the covariance function, and the second of the mean function. And then the rate should depend on both. If you make a comparison with regression, when you estimate regression with unknown variance, there's a completely different problem from that when the variance is known. So both the smoothness of the variance function, the smoothness of regression.
Yeah, that will be the same here, because of course this depends. I can go back to the estimator, then you can see, let me see, where was it? I didn't write the estimator exactly, but here is the general formula. So what you have to do is in order to fit this trajectory, we are calculating this conditional expectation, right? And so theoretically you can calculate, the formula is here. And what you need then, you can see the elements you need. There is an eigenvalue, which is well behaved usually, eigenfunction, and the mean function is here. These are all functions, right? So there's a mean function, it's a discretized, but you need basically you need a mean function as a function to get this result here, because it's at random. You evaluate this at the random points ui tilde. The mean is the same, and then you also have the covariance of your data here, which itself requires you to get a good estimate of the covariant surface, the kernel, and of the error variance. So you need all estimates of those, and the overall convergence rate, of course, depends on the individual rates. They come together, as you say. And so the property of G, the surface, the property of mu, the mean function, and even how well you can estimate the variance along the diagonal or whatever method you use for that, they all come together in this. And so the limitation, in fact, the main limitation is the G, because that is a two-dimensional function to estimate. So that's the main limitation. The lambda is faster rate, the sigma square is faster rate, the mu is a faster rate, the G is the one which basically determines the rate of convergence in that regard. So the limitations the limitation really, actually I should say, is on G, the kernel, how well you can estimate a kernel.
Doesn't that really sort of depend on the fact that you're assuming a bounded number of points on each curve? You could conceive of an asymptotic theory where you both let the number of curves increase and the density of the points.
Yeah, we have done that, yes. That's the result which, well, there are actually two results along these lines. Yes, exactly. So one result is that this whole aggregate stuff here converges to the integral. So in fact, this thing is just in the limit. If you take the quotient, let's say, of this, and the integral, the quotient converges to 1 in probability, which means that this is an integral in disguise. If you have many points, this conditional expectation tends to the integral. In fact, that justifies to use this method also in the dense case, because it gives you the same. And the second thing is you can think about the rate of convergence from the sparse case as compared to the dense case. What's the difference? And that actually we have done in a paper, in a 2006 paper, where basically you look at where is the limiting behavior between the sparse case and the dense case. There is some sort of a transition phenomenon. There is a really sparse asymptotics in one corner, and there is a dense asymptotics in another, where you have the UI, the number of measurements, going above a certain threshold. And then you get a dense asymptotics with better rates. So there are two scenarios which have been identified. There may be more in the middle between the two. So there's sort of a transition from sparse to dense. And the two asymptotics are very different. I mean, that's basically the point I'm trying to make. The dense case and the sparse case are different from each other. And they have different characteristics, sort of.
The reason that I thought of that also is because, say, if you think about asymptotics as spatial situation, then of course the dense case is typically the one that people focus on, right? You get more and more points in a given area. But it also may make some sense to think about the area increasing at the same time. Of course, then you don't have quite independence, but you have near independence, and you assume that the distant things have little to do with each other. And so that kind of asymptotics makes sense in other contexts in this
Yeah.
time series concept.
Yeah, it's interesting thought, yeah.
You said there was more than one way of calculating R squared. Do you have any experience about whether or not they give similar values?
The values are not all that similar. I mean, they give you sort of a similar ballpark, let's say, but I showed here an example where this one gave 0.55 and another one would give you maybe 0.4 or something like this for the same data. We chose this one not because it gives the highest R square, but because we have a nice mathematical representation for it as a weighted R square of the individual ones. So it seems to be sort of canonical to do a weighted averaging of those. That's one reason, and also the mathematics is just nice of that. The other one is very messy. You can also show the other one is you get consistent estimation for alternatives, but we didn't find a mathematical canonical one which looks nice and has a sort of statistically convenient interpretation as this one has. So that was the reason we chose this one over the others. But I don't know whether that's a good reason. I mean, there's a real ambiguity about the R square here in this case. So.
Thank you again.
Thank you.